Welcome to the course on audio signal processing for music applications. This week we're talking about how to model sounds by combining the sinusoidal or harmonic approach that we talked in the previous weeks with the idea of a residual or stochastic component. And the core aspect of that is how to subtract the sinusoids of a sound from the actual sound. And this is what we're going to be talking about in this programming lecture from a programming perspective. So we're going to be implementing the subtraction of sinusoids from a signal. And we're going to do it through the hprModel, the implementation of the model that we have within the SMS tools package. So basically we're going to be talking about this block diagram in which from the input sound and all the analysis that we have already been talking about, the computing of the spectrum, detection of the peaks, in the case of the harmonic models, detection of the fundamental frequency and identification of the harmonics. Then we are synthesizing these harmonics in the spectral domain, so we are synthesizing the lobes of the harmonics. And now in this week, what we are focusing on is on this subtraction. So we're focusing on how these sinusoids can be subtracted from the original signal. And what we do is we compute again the spectrum of the input signal with the same parameters, so therefore with the same window that is implicit, or in fact is quite explicit in the spectral domain of these sinusoids, so that then we can subtract them, and then this residual spectrum can be summed to the harmonic spectrum and obtain the time domain synthesized signal by combining the two. So let's look at some code that I wrote to show this in a concise way. So I wrote some code that just does it for one single frame. So first we import all the packages that we need for this analysis. Okay, we already have seen all of these packages. And then we read a sound file. So we're going to start from the oboe sound, the A4. And we need to specify some parameters. In particular, we're going to be analyzing only one frame, so we choose the location, the pointer where we're going to be reading the sound from, so the place 40,000 sample. Okay. And then, well, we need a window size M. We take 801 samples. We need an FFT size bigger than that. So we take 2048. Then we need a threshold for identifying the peaks. Since we're going to be doing harmonic analysis, we need the minimum and maximum frequencies to look for the fundamental frequency. Then we need an error threshold to have the lower bound for the algorithm that we are using for F0 detection, the two-way mismatch error function. Then we will decide how many harmonics, the maximum number of harmonics that we are going to be identifying, and this is the deviation slope that we choose, so that the higher harmonics have a higher degree of deviation than the lower ones. Okay, so these are the parameters, and now we start by computing things. So first we compute the analysis window, and we take the Blackman window. Then since we're going to be doing this subtraction, the phase information is fundamental. We need to do zero phase window. This is where is fundamental the idea of centering everything around zero, so that the time domain basically waveforms, they align perfectly so that the phases match, and therefore the subtraction is possible. And here the odd size window is again fundamental, so that's why we need to compute the center of the window in this way. Okay, then we choose the fragment of the sound. and here the pointer, so we choose the center of the window. The pointer is the center of the window, and we take half of the samples from the left of this pointer and half of the samples on the right of this pointer. Okay, so this is going to be our sound that we analyze. And then we have seen all this before. We compute the DFT of this fragment of the sound. We find the peaks. We interpolate the peaks with parabolic interpolation. In here we convert locations to hertz. And now we detect the fundamental frequency. Okay, so we call the two-way mismatch algorithm, and it returns the best candidate for fundamental frequency. And we identify all the harmonics by calling the harmonic detection function that looks for the peaks that are closest to the multiples of the fundamental frequency. Okay, and now we can synthesize these harmonics that we have identified, and we synthesize it with another FFT and window that we did the original analysis. So now we take an FFT of 512, and half of that is 256, and we're going to be synthesizing the spectral signs, so the main lobes of the Blackman window. Okay, and this is the YH, is the complete spectrum of this harmonic component. And now this is what we are basically focusing on this week. We have to subtract these harmonics from the original signal. But to do that, we need to recompute the spectrum of the original signal so that we use the Blackman-Harris window that is in this spectrum. Okay, so we have to compute a window, a Blackman-Harris window of the size of the same size that we are now using for the synthesis, 512. And then we're going to choose again from the original signal the fragment of the sound, but only the 512 samples around the pointer. So here we choose another original signal with these 512 samples and multiplied by the Blackman-Harris window normalized, so that then it becomes easier to compute to do the subtraction. Okay, and so this is our new input signal, and then we have to zero phase window it, so we have to put it around 0, and we do that by defining the FFT buffer we're going to use and center everything around 0, and then we can compute the spectrum of that. And the subtraction of the sinusoids then becomes easy. It's just a complex subtraction. We subtract the harmonics, the harmonic spectrum, from this new spectrum that we just compute. So, okay, so let's run this and let's step through the different variables that we have been generating. So this is the file called test3. Okay, so this has computed it. And now let's keep looking at the different variables. So for example, let's plot the X1 sound. Okay, this is the fragment of the sound we are analyzing. Okay, then we can plot the resulting spectrum that we computed from that. So we can plot MX. Okay, so this is in dB the magnitude spectrum of that. Then it has computed out of that peak, so we can even just print the locations of the peak. So EP log is the peaks, are the peaks that it has found within the array of the FFT. It's better to show it in hertz. So if we print IP frequency, is the frequency of the peaks it has found. Okay, then this has gone to the F0 detection. So it has identified the fundamental frequency, and the fundamental frequency has been chosen to be 443 hertz, which makes sense. Here we are analyzing a noble sound, an A4. And then out of this fundamental frequency, it has chosen the peaks that are harmonics of these. So H frequency is the set of harmonics that it has identified in this particular location. So it has identified all these harmonics. The other peaks have not been considered harmonics. Of course, we have chosen a threshold and a given set of parameters that has limited the number of harmonics to these 6,000. So it becomes easier. So we just have analyzed up into this harmonic. Okay, then we generate these harmonics as a spectrum, and so it has generated YH. So if we plot the absolute value of YH, we're going to see the magnitude of the complete spectrum. But let's plot it just in dB. So we will just plot in 20 times log 10 of the absolute value of YH. And let's just take only, let's say, the first 70 samples. So from the beginning to the sample 70. So we focus on the first harmonics, which are the ones that basically we have generated. Okay, so these are the harmonics that we have synthesized. This is the synthesized spectrum. On top of that, we can plot the signal that from the original sound that we have recomputed. So X2, the X2 spectrum. Okay, so if we plot on top of that the absolute value of X2, in here we now see the green line, which is basically the original spectrum, and as you can see is very much similar. So that means that we very much have synthesized the original spectrum. And then we can plot the subtracted spectrum. So the subtracted is the XR spectrum, and this is this red line. Okay, so the red line is the subtraction of the two, and it clearly shows the residual that it has. Okay, so this works, and basically we do that at every frame, and then of course we can do the inverse to generate all these signals back. Now let me show you the actual code that is in the SMS tools package that performs this harmonic plus residual modeling. So there is this file called hprModel.py within the models directory, and in it there is the analysis and synthesis of HPR modeling. There is one function that does the analysis, another one that performs the synthesis, and then there is another one that does both the analysis and synthesis at one frame at a time. In fact, we recommend very much to do the analysis and synthesis separate so that we can take advantage of cleaning the trajectories and having some memory in the tracking so that the harmonics are better. And in the analysis part of the function, it basically calls two functions. One that we already have seen. It does the harmonic analysis in the same way that we saw it when we talk about the harmonic model. And then the new thing that it does is the subtraction. So there is this function, sine subtraction, that has as input the harmonics identified by the harmonic model, has as input also the input sound again, and it subtracts the harmonics from this input sound. So this function is in the util functions directory in the file, and in here you'll find the sine subtraction function, and it basically does what I have explained just a while ago. It goes through the sound, and then at every frame it does the subtraction of the sinusoid. So the sinusoids have already been identified, so here it iterates over all the analyzed frame, and then it reads again a fragment of the input sound, it recomputes the input sound with this window, with the Blackman-Harris window, and then it synthesizes the harmonics with this Blackman main lobe, and then is able to subtract the harmonics from the input sound. And that's all. And then it synthesizes the residual signal back and undoes the windowing effect, so we can do the overlap at correctly. And that's all. That's what the sinusoidal subtraction does, and it returns, of course, the residual signal. And the output of the analysis is the harmonic frequencies, magnitudes, and phases, and this residual signal. And then the synthesis, it basically receives back the harmonic magnitude and phases that we analyze and the residual signal, and simply puts it together. So it calls the sinusoidal model synthesis that we already have seen, and it simply adds these sinusoids with the residual. And that's all. Then we have this other function, hprModel function.py, which is the file that puts it all together, and is in fact the file that is called from the interface that we have been using. And it's simply there is one function, main, and that does the analysis and synthesis of a sound, and it plots the intermediate values. So it calls the hprModel anal, okay, and then well, it computes the spectrogram of the residual so that we can show it as a spectrogram, and then it performs the synthesis, and it generates the overall output sound, the sum of the residual plus the harmonics, and just the harmonics, and it writes the files into the same directory. Okay, so now we can execute this file. We can run this hprModel function file, and it will analyze a fragment of a saxophone sound, which is the default sound, with the hprModel. So we will get, here we see the harmonics of the sound, and the background is the spectrogram of the residual. So we have computed the spectrogram of the residual, and here are the two together. And of course we can listen to them. We can just, in this directory, it has saved the residual signs and the sum of the two. So we can just play for example, first the residual, okay, and then we can play, for example, the sines, and we can play the sum of the two. Okay, and that's all. Basically, we have gone through the harmonics plus residual model, and we have used quite a bit of code from the SMS tools and from Python to be able to subtract the harmonics from the residual. And hopefully that has given you a programming perspective to this idea of harmonic plus residual subtraction. And it's not a very sophisticated thing from a signal processing point of view, but from a programming point of view, it's quite delicate. We have to be very careful in how to put the signals and how to analyze them in order that they align perfectly, and in order that the complex subtraction in the spectral domain is done correctly, and we obtain a real residual. And that's all. So in next class we're going to take the next step, which will be to from a programming perspective look at the stochastic component. So how we can then convert this residual that we just computed into an stochastic component, and then have the harmonics plus stochastic model. So see you next lecture. Bye bye.